But now we're going to look at an entirely different thing to terminate our discussion today, and that is, what is this estimated weight function? Remember that D was our original data, and what we want to do is assign large numbers to accurate data and small numbers to inaccurate data. Now, the right thing to do by statistical theory, which is what we will do, is to assign the reciprocal variance of each data point as the weight for that data point. So 1 over the variance, and the variance is the square of the standard deviation. And it doesn't matter what you multiply by, because as long as all the weights are proportional, the curve fit will be the same. In this case, we multiply by 1 over the square of the number of data points. This is because it's the nicest way of making a weighted fit kind of correspond to an unweighted fit in which the weights are all 1. If variance of y, you see, was 1, then this would be 1 over the number of points squared, which is just treating every weight as 1. Okay, now, the standard deviation is therefore computed as by unreciprocating this and computing its square root. The standard deviation is the square root of the variance, so the standard deviation is approximately the number of rows of data times the square root of the reciprocal of the estimated weight that we compute. Continuing down, we're going to look at a picture of that and look at what MLAB thinks the error in this data is. So, skipping fairly quickly past that, here is what MLAB thinks the error is. These vertical bars are 1 standard deviation, plus or minus, of each data point. Notice that this error at the beginning is fairly large, and as we get out here to the end, where these points kind of cluster closer together, this error is smaller. Notice this is fairly large because it deviates somewhat. This is not as large as that. And the way we compute this is with a moving standard deviation calculation that basically says, assume the error in a small neighborhood of data, this point, this point, this point, this point, is not too different, and use that information versus a certain kind of smoothing function to compute the differences from, to compute the standard deviation. So it's a fairly elaborate calculation, but it's very useful, and it's much better to use weighted data than unweighted data. If you use unweighted data, you probably will be giving much more attention to the erroneous points than you should. So,
okay. Very good. Gary, when MLAB figured out a fit here, could there have been more than one solution?
Sometimes the answer is yes, absolutely. There's no guarantee that solutions, the sets of parameters that make a model give a best fit, are unique. You can have K1 and K2, for example, and you might be able to increase K2 by doubling it and fix that problem by decreasing K1 by a half or something. So you never know if it's unique unless you look at those dependency values that we've talked about.
And what does MLAB do when there's multiple solutions? Does it give you the first solution? Or?
Essentially, it gives you, you might say that, yes, it gives you the first solution. And MLAB actually goes downhill on the sum of squares surface to find a minimal point. And it stops when the change in going downhill is 1 in 1,000. Now, you can control that with a control variable, which we haven't talked about today, but essentially MLAB will converge to a point where the parameters are not giving an improved sum of squares, and it will stop there and say, this is your answer. There's no guarantee that that's unique. You have to investigate that yourself to know that for sure. And there's no guarantee that it has physical meaning. You have to investigate that.
Of course. So in principle, you could set the tolerance differently, and it would keep searching for information.
It would keep searching, but of course, at some point, there's really no point to that, because the minute you find, either you will have a good unique fit a unique point in the parameter space, in which case 1 in 1,000 is probably perfectly good. Or you won't have a unique point, and even if you do it in 1 in 10,000, it still won't make anything unique. It just is not unique.
Very good, very good. So what we did here, Gary, in summary, was we applied MLAB in what way?
Well, what we did is we took data from the lab, we took a mathematical model for that data, which happened to be a differential equation describing second-order binding. We used MLAB's curve-fitting ability to compute parameters we did not know, K1 and K2, that we wished we knew, and made an estimate. If we had done this in real life, we would have taken further experiments. We would have used that to try to minimize the error in our data by computing averages, perhaps. And we would have come up with a pair of numbers that we could claim were statistically reliable and include that in our report of this experiment.
And is this the kind of thing that goes on every day in chemical labs across the country?
Well, it's certainly not the main thing, but it is certainly an important thing, yes.
Yes. And this ability to model and to fit, is that crucial?
It's crucial in a number of ways that have nothing to do with chemical kinetics. There are models for NMR machine output. There are models for compartmental models in pharmacology and toxicology. There are models in physics and in just about all the sciences, and even in the social sciences as well. There are mathematical models that people introduce to describe data and to predict the behavior of the world.
Okay. And as we hopefully over time we will produce more of these videos, and we will illustrate other domains and other modeling applications.
That would be nice. I hope we do that.
Alrighty. Thank you very much, Gary. This was great.
You are welcome. Thank you all. And I guess we should say one more thing, though.
Oh.
You should visit some website to learn a little more about MLAB, just in case you haven't done that.
Yes, we will put on a little bar on this video, which will pop up now. And when you click on that, you will be led to our website.
Wonderful. Okay.
Thank you very much.
All right, let's turn this off. And guess how you turn MLAB off? You finish the do file. A little more comments for you to see there, by the way. And then we say exit.
And that's it.